So now we're going to look at Euler's method. This is a BC topic, page 106. Euler's method provides you with a way to solve differential equations numerically. It is a technique for approximating the solution of an initial value differential equation. Euler's method for solving a differential equation is based on the fact that a differentiable function has local linearity at any given point. You can calculate the slope at any given point and follow the linear function to another point delta x units away. This is called a step. So the basic idea behind Euler's method is to start at your initial point, x naught, y naught, draw a line segment in the direction determined by the direction field until we reach the point x1, y1, and now we have the new coordinate x1, which is x naught, the initial coordinate, plus however much x changed. If delta x is small, then it is reasonable to expect that this line segment will not deviate much from the original curve, and thus y1 should closely approximate y of x1. To obtain subsequent approximations, we repeat the process using the direction field as a guide at each step. If you connect the resulting points on a graph with line segments, the result is a piecewise linear function that approximates the solution to the differential equation with the given initial condition. What we're trying to do is get an estimate of what our y value is in the real solution. In the real world, you would not use this method to solve the equation, but there are times in the real world where we know the rate of change, but it cannot be solved because we don't know how to do it. This is a way of estimating the y values for a function by using a tangent line approximation to get a point and repeating the process, an iteration technique. So you have here a worksheet, and we are going to actually work through problem number 4. Start at point 0, 0 and calculate the slope at that point, then assume the graph is linear between 0 and 1. Use the point slope form of the line at 0, 1 to find the next y coordinate, the value of y to be at x equals 1. Repeat the process for x equals 1, 2, and 3. Construct a solution means to find the last y coordinate. Part B says, solve the differential equation with the integration technique you know. Notice that the actual solution is 1 unit off from our approximated solution. And part C, the error is our approximated value minus the actual value. So let's work this example. Here it is. This says, use Euler's method to construct the solution for dy dx equals x over 2. With the initial condition, my initial point, 0, 1, and delta x is 1. So I'm going to use 4 steps and then sketch our solution. Since delta x is 1 and I'm starting at 0, I'm going to list my x's. I know my initial y is 1. dy dx is x over 2, so 0 over 2 is 0. Now, my point slope form of my line, y minus y1 equals m times x minus x1. The y1 and the x1 are my current point, 1, 0. Here's my slope, and I can find my next y coordinate. So my next y is 1. So when x is 1, y is 1. And I'm going to go through the procedure. dy dx, which is x over 2, is 1/2. My current x and y with the slope, do the work. The next y is 3/2. So when x is 2, y is 3 over 2. I'm going to go through the same process again. dy dx is x over 2, so my slope in this interval is going to be 1. Substituting my current x and y and the slope, find the next y to be 5/2. Next y is 5/2. My slope is x over 2, point slope form of my line. My next y is 4, and I am done. I don't do any more. Let's go back to the instructions. 4 steps. 4 steps means starting with the original, 1 step, 2 steps, 3 steps, 4 steps. Once I get to my 4th approximation, we're done. So let's look at a graph of this. Here's my initial point, 0, 1. My slope going to the next point is 0. It got me to the point 1, 1. My slope going to my next point of 2 and 3/2 is 1/2. My slope going to the next point is 1. It got me to the point 3 and 5/2. And my next slope is 3/2. and it got me to the point 4, 4. Part B says to solve this equation, and we have our initial condition. So first, I'm going to separate variables. Anti-differentiate. This side is going to give me y. This side is going to give me 1/2 x squared over 2 plus my constant c. There's my initial condition. When x is 0, y is 1. We get c to be 1. And there is my function that goes to the point 0, 1. In this part of the problem, it says to use this to find y of 4. So y of 4 would be 1/4, 4 squared plus 1, which is 4 plus 1, which is 5. Now, our estimate was 4 using Euler's method. Our actual value at 4 was 5. My Euler's method approximation at 4 was 4. How could I get a smaller error using Euler's method? What do you think? Guess what? Smaller steps. Maybe let delta x equal 0.5. So we have done problem 4 on this page. You will do the others. And nifty, here are the answers. Here's another slope field you can do. On pages 108, A, B, and C is some information from another text, which is really nice. Hughes Hallett text. And we can see that we've got a nice worked out problem, what the curve actually looks like, what the Euler's approximation gave us. And here there's a little discussion about the accuracy of Euler's method. Your TPs are in the textbook, just problem number 69. See you next time.